Hello everyone, my name is Yan-Shu Huang. I am a PhD student at Purdue University. I am working with Professor Gonzalez, Professor Nudge, and Professor Flowrates. Today, my presentation topic is real-time monitoring of powder mass flow rates for MPC-PID control of a continuous direct compaction tablet manufacturing process. These are the contents that this talk is gonna cover. In the beginning, we'll start with the background of continuous manufacturing and the motivation to investigate powder flow measurements. Then I'll introduce another sensor, the ECPD sensor, which is the first capacitance-based powder flow sensor implemented in the pharmaceutical manufacturing line. Finally, both simulation and experimental study will be used to demonstrate the benefits of mass flow monitoring in control applications. Currently, the pharmaceutical industry still relies on batch process to produce most drug products. To make sure that the final products have good qualities, all the intermediate materials have to be tested offline before they can transfer into next unit operation. However, if samples' qualities don't meet the regulatory standards, the whole batch must be discarded because there are no corrective actions can be done at all. The only solution is to reproduce a new batch. Therefore, to use the materials more efficiently, the pharmaceutical industry is trying to shift from batch to continuous process. You can imagine that if all the sample quality can be measured online and off-spec materials can be detected, we can correct the process in real time so materials can be used more effectively. Therefore, using sensors to capture process dynamics and have active control strategies are two key factors in continuous manufacturing. In continuous tablet manufacturing line, the raw materials are delivered by those in wave feeders at first. Next, the powders are mixed via the blender. Then, depends on different procedures, we have direct compaction, dry granulation, and the wet granulation process. Finally, the powders are fed into the tablet press, and the tablets are produced. Basically, tablet manufacturing is a particulate batch process. You can imagine that rat holing, bridging, and powder leakage can affect process performance a lot. The question is, how do we monitor this phenomenon? The answer is mass flow monitoring. Compared to batch process, mass flow rate is a new variable in continuous process. Mass flow rate is a critical parameter which can affect CQA like API concentration. We also have to use flow rate to check if there are any powder accumulation or powder leakage in the process. However, most of the time, we only rely on the readings from those in wave feeders, so only the upstream flow is known. Therefore, we should investigate the mass flow sensor to capture the flow dynamics in the whole process. Here is the novel sensor I am going to introduce today, the ECPD sensor. From the picture, we can find that the sensor is pretty compact and is easy to locate on the pipe. In addition, the sensor calibration is much simpler than spectroscopy sensor because no PLS regression models are required. The sensor is widely used in dynamic behavior visualization in fluidized bed, but we used it for mass flow monitoring in this study. One thing to be noted is that this is the first capacitance-based sensor used in continuous tablet manufacturing line. To measure the powder flow rate, the volume fraction and the velocity are required. The physical principle behind the ECPD sensor is based on parallel plate capacitor. Considering the difference between air permittivity and the powder permittivity, we can find that the capacitance is proportional to the volume fraction of powders. By cross-correlation of both capacitance signals from the top capacitor and the bottom capacitor, the velocity is calculated. Let's look at the result of the sensor calibration. From R square value is equal to 0.98 and the Roomy square value, we know that the linear fitting works well for the range from 2 kg per hour to 10 kg per hour. Some common pharmaceutical powders are also tested. The prediction errors are affected by powder properties. The powder with better flowability has lower measurement error. After the sensor calibration part, let's see how mass flow measurement can affect control performance. For the control strategies, a hierarchical three-level control structure is applied in this study. Basically, level 0 control is equipment-based control. The controller type is simple PLC. We can use it to manipulate CPP, like rotation speed of the blender, dosing precision of the tapping press. That is, level 0 control is just for open-loop operation and limited to one unit operation. Level 1 control is PAT-based control, which means we need additional sensor measurement so the CQA can be controlled in a closed-loop operation. The controller type in Level 1 is PID controllers. Level 2 control is model and optimization-based control. The controller type is model predict control (MPC). If the plant-wide system is complex and the process interaction is strong, Level 2 controller can stabilize the control objective better than Level 1 PID controller. The dynamic flow sheet modeling is performed in MATLAB Simulink. In the figure, the blue lines represent the direction of materials flow, and the red lines represent the direction of measurement flow and the control commands. The flow sensor and the API compensation sensor are both located at the exit of the blender. All the measurements are sent to the DCS. Based on the measurements, the DCS will send the control commands to Level 0 PLC controller. The details of the DCS is shown in here. For Level 2 MPC, it's MIMO system. For Level 1 PID, it's SISO system. So that's why we need several Level 1 PIDs here. To be clear, a table is provided here. In this study, 6 input variables and 6 output variables are included in the direct compaction line. To maintain CQA within the tolerance limits, the controller should be able to deal with risk scenarios. In this section, we introduce a feeder calibration error that the actual excipient flow rate is 20% lower than the reading from excipient feeder. Now, we want to compare 3 kinds of control structure. First, it's an open-loop operation. We directly manipulate each equipment. Second, it's a closed-loop operation. We use the API concentration measurement and the ratio controller to control the API feeder, which is a common strategy. The last one is also a closed-loop operation, but an additional flow control loop is considered, as you can see in the blue dashed line. Let's look at the results. The open loop operation, the pink line, fails to maintain the API concentration with the tolerance limits. By contrast, the corrective actions are done in closed loop operation. If we look at the brown line and the blue line, we can find the closed loop with flow sensing can correct the API concentration the most efficiently and have the fewest variation in powder flow rate, tablet weight, and the Harper level. To quantify the control performance, some indicators can be used. OS time means the period when the CQA is now within the tolerance limits. D2R is the time that the process requires to smooth out the process disturbance. And 2P is the maximum deviation in the CQA from the target set point. ITAE is integral of time-weighted absolute error. Smaller indicator values mean better control performance. From the table, it's clear that the closed loop with flow sensing demonstrates the best control performance, especially when we look at the OS time. The reduced 30 seconds can save 400 more tablets compared to the closed loop without flow sensing. A good control strategy should be able to reject disturbance as well. Here, a sine wave is added to the powder flow rate at the axis of the blender to emulate the disturbance. We know that the turret speed is an important CPP in continuous direct compaction line. In conventional approach, people use upper level to control the turret speed, as you can see in the brown line. Although the upper level can be controlled around the set point, the frequent change of the turret speed causes variation in the tablet weight. By contrast, if we choose to use the production rate to control the turret speed, as you can see in the blue line, the variation and the tablet weight are reduced. To further investigate the choice of control pairings, RGA analysis can be used. When the production rate is used to control the turret speed, the diagonal elements in the RGA matrix are close to 1, which means the MI-MO system can be decoupled into many SI-SO pairings, and the control system is stable. However, if we choose to apply the conventional method to use the upper level to control the turret speed, the element in the RGA matrix deviates much from 1. This means that the control system is unstable and cannot be decoupled into several SI-SO pairings because of strong process interaction. When considering different API concentration, we can find that the level control method results in a more unstable system when the API concentration is decreasing. With more real-time measurement, the advanced level 2 control strategies can be applied. Step changes are introduced into both API concentration and the tablet weights to produce process interaction. Now, level 1 PID, level 2 MPC, and the level 2 nonlinear MPC are considered. For the ability to set point tracking, level 2 nonlinear MPC demonstrates the quickest response compared to others. For ability to reject the disturbance, we can look at the compression force and the production rate. We can find that both MPC and the nonlinear MPC have better control performance than the level 1 PID. The control performance are quantified in this table. Overall, nonlinear MPC has almost the best control performance, as you can see that the rise time and the fall time of set point change are the shortest. Since that we have demonstrated the benefits of flow measurement, let's move on to the experimental implementation. In the beginning, this is the feeding blending system. The mixed powder will pass on the ECPT sensor, then go to the tablet press. The tablets are collected on the weighing scale, and the real-time production rate can be captured. Inside the compartment of the tablet press, a webcam-based level sensor is used to monitor upper level. In the photo analysis software, we can define the range of the box by ourselves. In this study, the range is roughly 18 cm. In case study 1, only excipient feeder is used. The top figure is the reading from the nose in-way feeder. The middle one is the ECPT measurement. The bottom one includes tablet production rate and upper level. Before time is equal to 300 seconds, there is offset in the flow measurement from the ECPT sensor. After the level 1 closed loop is applied, the offset is reduced, and the step change can perform well. In addition, by controlling both the powder flow and the production rate, the upper level is indirectly controlled as well. When powder flow is equal to production rate, the level is constant. When we let the production rate is higher than powder flow at time is equal to 400 seconds, the level starts to decrease. One thing to be noted here is that when the tablet press stops when time is equal to 600 seconds, the production rate is dropped to 0. By monitoring both powder flow and upper level, we don't have to shut down every equipment to prevent powder accumulation before we return on the tablet press. In case study 2, the API feeder is also used to feed materials. A ratio control is used to make the API concentration 10%. Due to poor flowability of API, the variation in the ECPT measurement is larger compared to one feeder case. Even so, The Level 1 supervisory control is still able to control the total flow. As you can see, a step change is introduced at time is equal to 500 seconds and time is equal to 800 seconds respectively. In conclusion, plant-wide control performance is much improved when real-time powder flow measurement is incorporated into the control structure compared to traditional strategies we use in the DC line. From the experimental implementation, this novel sensor is used to control and monitor the flow dynamics. In the future, we will keep working on implementation of Level 2 control and state estimation. I want to appreciate FDA for their funding support and Tech4Image for their ECPD sensor. Besides, I also want to thank our research group. These are some related Industry 4.0 talks in our group. Thank you for your attention. Please feel free to ask me any questions.